Hey guys, so in this video we're going to be looking at representing complex numbers as vectors in the complex plane. So first of all, what is a vector? Well, a vector is simply a measure of a quantity and a direction. For example, distance is not a vector, because when we measure the distance between two things, we have a quantity, but we don't take into account which direction one thing is relative to another. For example, if I have 3 points, A, B, and C, which are 4 kilometers apart like this, then the distance from A to C is the same as the distance from A to B, which is 4 kilometers. However, C is clearly to the west of A, while B is to the east. So while the distances are the same, the directions are not, and that's why distance is not a vector. However, complex numbers are vectors, because they have a direction, which is the argument, and they also have a quantity, which is the modulus. Now normally we represent a vector as an arrow. So say we have a complex number z, which corresponds to the point P in the complex plane. We can think of z as a vector by drawing an arrow from the origin to the point P. Another notation we use to represent z as a vector is O going to P, which we write as OP with an arrow on top. And here the O stands for the origin, while P is our point in the complex plane, and the arrow indicates that it's a vector. In general, if I have any points P and Q, then we write the vector from P to Q as P going to Q. Cool, so that's all the technical stuff. Now let's get on to the maths. We can also have negative vectors, and these correspond to the arrow going in the other direction. So if I have a negative vector, negative O going to P, that's the same as P going to O. And the reason why this is so is because if I have a complex number z, or in this case a plus bi, then when I take the negative of z, I get negative a minus bi, which will lie somewhere here in that complex plane. So the vector of z goes in this direction, while the negative vector of z goes in the opposite direction. But as you can see, if we were to shift this vector and place it on top of this one, we'd get the same as the original, but going in the other direction. So in general, if I have a vector, negative p going to q, that's equal to q going to p. Simple. But the real useful thing about vectors is when you add them up. So say I have 2 points in the complex plane, p and q, which will correspond to the complex numbers z1 and z2 respectively. But now say I want to find the vector p going to q. How can I do this? Well, all a vector means is that you start at P and then you end up at Q. So sure, I could go straight there, but I don't have to. I can also go this way, or that way, or this way, or that way, as long as I start at P and end up at Q. For example, starting from P, I can go to O instead, which is P going to O. But of course I need to finish at Q, so then I can go from O to Q, which means we add O going to Q. Now remember that P going to O is equal to negative O going to P, using what we just learnt about negative vectors. So we get P going to Q is equal to negative O going to P plus O going to Q. But now O going to P is just Z1, and O going to Q is simply Z2. So we get P going to Q is equal to negative Z1 plus Z2, which equals Z2 minus Z1. Now what about multiplication? Well, let's say we want to multiply by a constant real number, like 2, 3, pi, etc., etc. Now recall that multiplication was super easy when we had our complex numbers in polar form. So let's go ahead and change them into that. So let's say I have a complex number in polar form r cis theta, and now I'm going to multiply it by a constant which I'll call c. And so that's just going to be equal to r times c, cis of theta. So our argument theta doesn't change by doing this, but our modulus either gets longer or shorter depending on whether c is greater than 1 or less than 1. So in terms of vectors, this means that whenever you multiply a vector by a constant c, you get the same vector but either longer or shorter. For example, multiplying by 2 would double the vector's length. Multiplying by 3 would triple it, and multiplying it by half would halve it, and so on. Okay, but what if it wasn't a constant real number? What if it was, say, I? Well, in polar form, I is equal to cis of 90 degrees. So that means if we have any complex number r cis theta, and we multiply it by I, it will be the same as multiplying by cis of 90 degrees. And remember, whenever we multiply two complex numbers in polar form, we multiply their moduluses and add up their arguments. So we'll get r cis theta times cis of 90 degrees is equal to r times the cis of theta plus 90 degrees. So what this means is whenever I multiply by I just rotate my vector 90 degrees anti-clockwise. For example, if I take the vector O going to P, which represents the complex number Z, then multiplying by I will rotate O going to P 90 degrees like this in our complex plane. And now if I call this point Q, it's equal to I times Z, which of course equals I times O going to P. Now let's amp it up to the next level. What if I want to multiply by cis theta? So again, I have r cis theta, and just to avoid confusion, I'm going to call this new angle alpha. So we have r cis theta times cis of alpha, and that just becomes r cis of theta plus alpha. So just like before, this means that whenever we multiply a vector by cis of theta, we just rotate that vector by theta degrees. Easy. Right, so that's all the theory. Now let's apply it to some actual problems. Imagine we have a rectangle in our complex plane called OPQR. Now let's call this point Q the complex number Z in our plane, and we'll also add the condition that the longer side of the rectangle OP is double the length of the shorter side OR. Okay, so here's the problem. What is O going to P in terms of Z? Well, what do we know about O going to P? Well, looking at our rectangle, O going to P is the same as R going to Q, because they are parallel and they have the same length, since OPQR is a rectangle. Or in other words, they have the same direction and the same quantity. And since that is exactly what a vector is, they must be the same. So O going to P is equal to R going to Q. Right, so that's not getting us very far. But remember, the problem was to find O going to P in terms of Z. So maybe instead of focusing on O going to P, let's focus on Z instead. Now Z in vector form is O going to Q. But remember that O going to Q simply means that we start at O and we finish at Q. So using what we learned about the addition of vectors, we can start from O and then go to R instead, which is O going to R, and then from R we can go to Q, which is R going to Q. So O going to Q is equal to O going to R plus R going to Q. Or in other words, Z is equal to O going to R plus O going to P. Because before, we learned that O going to P is equal to R going to Q. Great, so this is progress because now we've got O going to P in terms of Z and O going to R. So now we just have to get rid of this O going to R and we'll have our answer. However, when dealing with vectors, we can't exactly get rid of one vector or another. What we do is we convert one vector into another. So really we have to convert O going to R into terms of either Z or O going to P. To do that, let's take a closer look at O going to R. Well, O going to R has a distinct relationship with O going to P. For one, we know that O going to P is twice as long as O going to R, and the direction of O going to P is the same as O going to R's rotated 90 degrees anti-clockwise. So that means using what we learned about multiplication of vectors, if we take O going to R and double its length by multiplying it by 2, and then rotate it 90 degrees anti-clockwise by multiplying it by I, then we get the vector O going to P. Great, so that gives us O going to R is equal to O going to P divided by 2i. Now we don't like this I on the bottom here, so let's get rid of it by multiplying the top and bottom by I, which gives us 2i squared on the bottom, which is negative 2, and I on the top. So in other words, we have negative I on 2 times O going to P, which is of course still equal to O going to R. Now let's go ahead and sub this equation into our other equation back here, which will give us z is equal to negative I over 2 times O going to P plus O going to P. And we're almost done. Now we just need to make O going to P the subject. And to do that, we take out O going to P as a factor of the right hand side, giving us O going to P times 1 minus I over 2 is equal to z. And just to tidy it up a bit, I'll combine the 1 minus I over 2 into one fraction, which is 2 minus I all divided by 2. And finally, multiplying by 2 and dividing by 2 minus I, we get that O going to P is equal to 2z all divided by 2 minus I. Awesome, nailed it! We found O going to P in terms of z. Now let's do another one, and for that we're going to need some more paper. Suppose in our complex plane we have 3 points P, Q and R, which together form an equilateral triangle like so. Now let the point R correspond to the complex number z1, and the point P correspond to the complex number z2. Now the question is, what is O going to Q in terms of z1 and z2? Okay, well let's start with O going to Q. O going to Q simply means we start at O and we finish at Q. So let's use our trick of adding vectors to go from O to R first, which is O going to R, and then from R we can then go to Q. So we have O going to Q is equal to O going to R plus R going to Q. Or in other words, since O going to R is just z1, we have z1 plus R going to Q. In that case, let's play with R going to Q on its own. Now notice that R going to Q is the same as R going to P, rotated 60 degrees anti-clockwise. So that means R going to Q is equal to R going to P times the cis of 60 degrees. But now we've got an R going to P here. But R going to P means that we start at R and we finish at P. But instead of going directly there, we can go from R to O first, which is R going to O, and then we can go from O to P, which means we add O going to P. And this is equal to O going to P minus O going to R by taking the negative vector of R going to O. But O going to P is simply z2, and O going to R is just z1. So we get that R going to P is equal to z2 minus z1. Now by subbing this back into our equation up here, we get that R going to Q is equal to z2 minus z1 times the cis of 60 degrees. And by doing the same thing back into this equation, we get O going to Q is equal to z1 plus z2 minus z1 times the cis of 60 degrees. Now the cis of 60 degrees in Cartesian form is half of 1 plus I root 3. And putting that back into this, we get O going to Q is equal to z1 plus half of 1 plus I root 3 times z2 minus z1. And that's it. We're done. We found O going to Q in terms of z1 and z2. That's all for this video, guys. Next time we'll be looking at representing complex numbers as vectors in the complex plane. See you then.